Next, I'm going to talk about how to carry out a statistical mediation analysis procedure using 4 different approaches in R. The first approach, which you're unlikely to prefer, just sets up the regression models individually and calculates the indirect effect using bootstrapping with the boot package from the Comprehensive R archive network. So let's briefly review those 2 key regression models. I say 2 key regression models because we don't need the model with the total effect to calculate the indirect effect. All we need is the A path model and the B path model. So the first one uses legs to predict rating.fun and identifies that the discrepancy in rating.fun between robots with legs and robots with wheels is 0.987. And the second model uses rating.fun and legs to predict price and identifies that the slope of rating.fun adjusting for legs is 5.21. The indirect effect is going to be the product of those 2 numbers, 5.21 times 0.987. And of course, if all we needed was a point estimate of the indirect effect, we could just multiply them together directly. But we want a confidence interval for the estimate of the indirect effect. One way to get a confidence interval like that is to use the boot package to carry out bootstrapping yourself. And that package needs you to have a function that calculates the statistic that you want to calculate, and that can be used to calculate that statistic in each bootstrap sample individually. Here, I'm naming this function indirects1, and I'm defining it as a function that takes 2 arguments, a data argument and an indices argument, representing the subset of the data frame that I want to work with at any given time. And the function first creates a regression model called model_rating.fun that predicts rating.fun using legs, just as we did above, and another model called model_price that has the 2 predictors, rating.fun and legs, and price as the response variable, just as we did above. But both of these regression models include a data argument that retrieves the same data argument from the indirects function itself, and a subset argument that retrieves the indices given in the indirects function itself. Then this function calculates a slope estimate for the indirect effect by retrieving the legs slope from the model coefficients from the first model and the rating.fun slope from the coefficients of the second model and multiplying them together. And that's the value that it returns. What this accomplishes is given any data set and any set of indices, as long as these variables are present in that data set, it will give an estimate of the indirect effect. Next, we carry out the bootstrapping using this boot function from the boot package. And this function allows us to specify a data frame to work with, a function to use to calculate our statistic, that's indirects1, and a number of bootstrap samples, that's 5,000. This is why the function needed to have arguments for data and indices. The boot function handles the process of generating a new set of indices for each bootstrap sample, but I have to provide the original data set. Then I can calculate a bootstrap confidence interval using the boot.ci function from the boot package by plugging in the results of the bootstrapping procedure from here, with an argument specifying that I want the confidence interval to be a 95% confidence interval, and I want to use the type that's called BCA, because that's sort of the gold standard as long as it's available in any given statistical package. The results of this procedure look like this. This is the summary information that's given when you print boot results to the console directly, and this is the boot.ci output, which I've named boot_ci. The key information here is that the statistic that we're calculating in the overall sample is 5.145. That's our estimate of the indirect effect. And the confidence interval for that statistic using the BCA method ranges from 3.343 to 7.091. In this case, I used 5,000 bootstrap samples, which is a perfectly fine default in most cases. Okay, the next example I want to show you uses the package Lavon from CRAN. This is a general package for structural equation modeling. So I'm just showing one application of it here. This is usually my go-to strategy for doing statistical mediation in R, because it is general, so I can then use the same package that I'm already familiar with for other kinds of structural equation models too. The way this package works is you have to first prepare a description of the set of models you want to run, the structural equation model, before you even call any functions. So this might look like a lot of information, but this is just one long string variable called model specification. I'm using the equal sign as the assignment operator, and then everything in between this quote sign and this quote sign is just part of the string. These plus signs are not part of the string. They're just indicating that R is aware that I have not finished giving it its instruction yet, because I never closed this quotation mark. So this is a string that has 3 important lines in it. The first line is a description of one of the regression models. The second line is a description of another regression model. And the final line is a specification of a statistic that I want to calculate. The way this syntax works is each line that represents a regression model should start with the name of the response variable in that model and then a tilde. And then you can have your predictors separated with plus signs like usual, except that you're allowed to give names to the individual slopes for the predictors. So this A asterisk does not mean that I'm including an interaction term between something called A and legs, like it would mean in the LM function. Instead, the asterisk means that I am naming something, naming the slope of a variable. So A is the name that I've given to whatever slope it ends up calculating for the legs variable in the model predicting rating.fun. And in this next line, I have a slope for legs. I didn't feel the need to give that one a name because I'm not going to use it. And a slope for rating.fun, and I have given that one a name, and that name is B. After I've specified these 2 regression models, then I have one more line that has a fancy symbol in it, this colon equals sign. And that means I'm defining a new variable called indirect that is defined as the product of A and B. So in this definition of a new variable, the asterisk goes back to meaning multiplication rather than naming a slope. And given that I've already assigned names to the slope of legs in this model and the slope of rating.fun in this model, I can then use those names in the multiplication that defines this new value indirect. I called it a variable a second ago, and that is an okay way to refer to it, but maybe a better way to refer to it is as a statistic that I want the Lavon package to calculate for me when it fits the structural equation model that I've defined here. The next step is to fit that actual SEM and do bootstrapping with it. And the function from the Lavon package that accomplishes that is just called SEM, all lowercase. And it expects to have an argument called model, that is this long string indicating the full model specification, an argument called data that provides the data frame we're working with. And here I've added the arguments SE and bootstrap, and I specified SE equals, quote, bootstrap, end quote, in order to tell SEM that I want it to use bootstrapping at all. And then the bootstrap argument specifies how many bootstrap samples I want it to draw, and that's 5,000. This function can take a little while to run, more so than some of the other functions I'm going to show today. And that's because it's bootstrapping a lot more than just the indirect effect that I actually care about. And so in some ways, this function is doing, like if I'm not going to use the bootstrap confidence intervals for anything else besides the indirect effect, then there's some wasted calculation going on here. But it's not really that big of a deal because it'll finish in a second. Then once model result exists, that is, once the SEM function finishes running and I have an object called model result, I want to call this summary function on that object, like we often do with many other statistical procedures. And then I get this lengthy output. Let's walk through it piece by piece. First, it tells me some information about the function that I called. It says that it's using maximum likelihood estimation for the slopes. That doesn't really matter in this case. It has some other information about the optimization method, and most of that doesn't really matter to us. Scrolling down, it is useful to remind ourselves that we asked for and received 5,000 bootstrap samples. Of course, it's not showing us the parameter estimate from each of the individual 5,000 samples, what it's showing us is some summary information about the model itself. And we don't have our key confidence intervals just yet, but it is nice to remember what regression models are included in this structural equation model, and make sure that makes sense. So this is the slope of legs predicting rating.fun, and these two slopes correspond to legs and rating.fun predicting price, and that's exactly what we wanted in this case. Then it has also estimated some variances of the variables that get used as response variables in at least one of the regression models. And for the sake of statistical mediation analysis, we typically just ignore that information. And finally, it tells me that the parameter that I defined, called indirect, because that's what I named it, has this value, 5.145, in the overall sample, which we already knew because we calculated it before in some of the other examples. This is the conventional SEM summary, but I asked it to do some bootstrapping, and so now I need to get the bootstrap confidence interval. The way to retrieve the confidence intervals based on bootstrapping from the output of the SEM function is to use this other function, parameter estimates, from the Lavon package. And I supply the model result as the first argument. But I also have to tell it what type of bootstrap confidence interval to calculate. And here the string that I provided for this argument is bca.simple, which unfortunately is just what Lavon calls BC, bias corrected, not accelerated confidence intervals from bootstrapping. So this is somewhat confusing because I said before that there's two main ways of adjusting the percentile confidence intervals from bootstrapping to improve them slightly. And the gold standard is called BCA, and there's this other one that's BC that is very similar, and it usually doesn't matter which one you use, but it's nice to know which one you're using so that you can report it accurately in your results. And this should just be called BC. But for some reason, the creators of the Lavon package called it bca.simple, and BCA itself is not available in this package currently. So just know that when you provide this argument, you're actually asking for BC confidence intervals, and that's what we get. We get confidence intervals for everything from the structural equation model. But the one that we actually care about is this final row that has indirect as its label, because that's what I named the indirect effect parameter when I specified the SEM instructions. And we already know that the estimate of the indirect effect is 5.145. But critically, now we have a confidence interval for that indirect effect, ranging from 3.377 to 7.109. And that's the information that you would report alongside the estimate of the indirect effect in your paper. Really the only information you need beyond what you already got from just looking at the regression models themselves. The next example I want to talk about uses the mediation package from CRAN. And to use this package, we have to first set up the two main regression models that we're going to use in the analysis as LM objects. So consistent with the nomenclature that I used earlier with the boot package, I've decided to call the first one model_rating.fun, and the second one model_price. The first one uses rating.fun as the response variable and legs as the predictor, and the second one uses price as the response variable and has two predictors, legs and rating.fun. Then I can run the actual mediate function from the mediation package. Here's the function call, mediate, and this function expects several types of arguments. The first one, model.m, is supposed to be an LM object that represents the model predicting the mediator in your overall mediation analysis procedure. So this is what I called model_rating.fun before, because that's the one that uses legs to predict the mediator, rating.fun. Then we have model.y, which is supposed to be an LM object that represents the full regression model predicting the final outcome variable in your hypothesized mediation relationship, and that corresponds to what I called model_price. Then you have to specify the names of some of the variables so that the mediate function can figure out which variables to retrieve from these regression models in order to carry out its job. And treat is the name of the variable that I've been calling the initial predictor variable or the manipulated variable. They call it the treatment variable. So treat is short for treatment, and that's legs. And mediator is the name of the hypothesized mediator, rating.fun. Finally, I provide the argument boot equals true to tell it to do bootstrapping in the first place, sims equals 5,000 to indicate that I want 5,000 bootstrap samples, and boot.ci.type to indicate what type of bootstrap confidence interval I want, and that's BCA. And in this case, it really is BCA. So this function, mediate from the mediation package, can provide you with actual BCA confidence intervals. To get the result, we just call the summary function on the object created by the mediate function, and we get a summary table like this. And at first, this can be sort of difficult to parse because it uses potentially confusing terminology to refer to the estimated values. So you just have to remember that ACME stands for what they call average causal mediation effect, which is what I've been calling the indirect effect. And that's why its value is 5.14, consistent with what the indirect effect was in all of our other examples so far. And it provides a lower and upper bound for the confidence interval, ranging from 3.4 to 7.11, and that is a 95% BCA confidence interval based on 5,000 bootstrap samples for this estimated indirect effect. That's really the only thing you need from this output, but also you get a bootstrap confidence interval of ADE, which is what it calls the average direct effect. That's the C prime path. The total effect, that's the C path, and something called prop mediated, which is one type of attempt to calculate a standardized effect size measure for indirect effects in mediation analysis. I'm not a big fan of it. What it does is divide the indirect effect, 5.14, by the total effect, 5.81, and that's why it ends up being 0.89 in this case. This prop-mediated statistic is supposed to represent the proportion of the total effect that is accounted for by the mediator, and if all possible mediators work in the same direction, then I suppose it could be interpreted as the proportion of the total effect accounted for by that mediator. But in general, that's a weird assumption to make, and I think it's misleading to say like 89% of the total effect is accounted for by the mediator in this case, because although it is true that the indirect effect is 89% as large as the total effect, that is, the indirect effect of legs on price via fun is 89% as large as the total discrepancy in price between robots with legs and robots with wheels. There might be some reasons why robots with legs are more expensive than robots with wheels, and other reasons why robots with legs would be expected to be less expensive than robots with wheels. In the next example, I want to show you how to use the process macro created by Andrew Hayes. And like Levon, this procedure calculates BC confidence intervals, not BCA. And this function process was created by the process.r code file that I downloaded from Andrew Hayes' website and ran earlier in this series of videos. You saw it doing its little loading screen thing a second ago, but here's the actual function call up here. The function is just called process, all lowercase, and you specify a data argument representing the data frame that the variables are going to come from. You give the names of key variables. The y variable is price, the x variable is legs, and the m variable is rating.fun. Then you have to specify a model number, which I'll come back to in a second. Tell it how many bootstrap samples you want it to generate, 5,000, and BC equals 1 is just the way of telling it to do bias-corrected bootstrap confidence interval rather than a percentile bootstrap confidence interval. Again, this function doesn't have the option to generate a BCA confidence interval. So I had to specify model equals 4. And for now, you can just make a note that model 4 is the one that corresponds to the type of mediation model that we've been talking about all along. Andrew Hayes has generated many examples of different kinds of mediation-related models and given them all numbers. And there's a key that you can download from his website that indicates which model number corresponds to which type of model. So there's not really an intuitive way to explain the type of model you want as an argument to this function. Instead, you just have to look it up in Andrew Hayes's key and notice which number corresponds to the circumstance you're working with. If you have one predictor variable, one mediator, and one response variable, then it's model 4, and that's the most common case, the only one that I'm talking about today. So the output of this function begins with some explanation of where the function came from, and then a reminder that we used model 4 and that these are the 3 variables. The sample size was 500. And then finally, we see some actual statistical output. And the first portion of it just shows the summary table from the regression model predicting rating.fun. The only predictor is legs. Then we have some regression table summary output from the model predicting price. That has 2 predictors, and we're already quite familiar with these slopes by now. Then there was this sort of loading screen thing that is finished now, and below that information, we have the results of the bootstrapping procedure. And the critical one is the estimate of the indirect effect, which, as always before, is 5.145. The confidence interval is what we got from bootstrapping, and that ranges from 3.45 to 7.13. And that's the information that you would typically report alongside the regression model output that you're already quite familiar with. At this point, it's worth noting that there is a package on CRAN called Bruce R, and that package contains a function called process, this time written in all caps. And that function is not the same as Andrew Hayes's original function, the most famous process function, although the Bruce R version of process does aim to mimic many of the key features of Andrew Hayes's function. So although I'm not demonstrating the process function from Bruce R today, you should be aware that it's yet another option to accomplish this kind of statistical mediation analysis in R. The main reason the process macro is so famous is that it's also available for SPSS, and for a long time it was one of the only readily available ways for SPSS users to accomplish this kind of statistical mediation analysis. And so I'm going to show you in the next video how to use the process macro in SPSS.